All right. Good morning, good afternoon, good evening to all of those attending today. I am Trey Walters. I am the founder of Applied Flow Technology, and current title is Chairman and Founder. And I want to talk today about an incident that happened 7 years ago that involved waterhammer in an alumina refinery. And we're going to look at this engineering accident and talk about what happened and what we can learn from it. So with that, let me get my a laser pointer here so I can go forward with that. Okay. So up in the resources area of the webinar, there is a technical paper. It's also on our website. And so what I'm talking about today came out of this this paper that was published earlier this year. So the title of the paper is "A Waterhammer Event in Alumina Refinery Causes Catastrophic Slurry Pump Failure." And there were 3 authors. So I want to make sure, and I'm the first author, and then my 2 co-authors I want to make sure that I give credit to here are Sam Chamberlain, who is AFT's channel partner in the Caribbean. He's with Carib Engineering. And then one of the engineers at the facility in Jamaica, Jamalco, Aval Robotham. And so they helped pull together the content of this paper. The paper was presented in April in Eindhoven, Netherlands, and that was the 14th International Conference on Pressure Surges. So if you're interested in reading the paper, it is, like I said, it's in the resources area. It's an interesting paper that that I wrote because normally when I'm talking about waterhammer, I'm talking about sometimes some math, some theory, some physics, and none of that is in the paper. There's no math at all. It's just telling a story of what happened, and there's some numbers in there to talk about the pressures that this facility experienced. What I also want to say is writing this paper was, in a sense, it was kind of the hardest and easiest paper that I've ever written. I've written about 30, and it was easy because of what I just said. There was like no theory, no math, no physics. It was just like text of explaining the story. It was hard for reasons that I'll talk about, but one of the technicians at the facility there in Jamalco was seriously injured, and it's something to remind us that waterhammer, a lot of people are they hear about that, and it's a little bit of a scary term because they don't understand it very well, but it can be very serious as far as safety on personnel, and that's what happened in this particular incident. Okay, so here's a summary of the accident. So on the morning of April 16th, 2016, an alumina refinery in Jamaica had a catastrophic failure. There was a manual discharge valve from the pump. It was about 7 meters, 23 feet downstream from the pump, and the valve stem broke, and that caused the valve disc to slam closed. And then immediately after that, the pump casing exploded, and the pump was carrying hot well, it was a slurry, so it was a water-based slurry, but it was caustic, and it was also very hot. And there was nearby personnel that when the pump damage happened, it sprayed onto that technician, and that technician, I said, unfortunately, he was severely injured, permanently injured, and so that is a sad story. And as engineers, we always hate to hear that happen. Especially something that we might have worked on. So how AFT got involved with this is soon after this happened, Jamalco contacted, and if I go back a page right here, they contacted Sam Chamberlain at Carib Engineering to come in and help with the assessment of what happened. And there were a number of factors that went in, and I don't need to get into that, but Sam contacted us, and myself and some other people here at AFT, and also the consulting company that we operate, Purple Mountain Technology Group, built some models back in 2016 to try to get a sense of what the waterhammer pressures might have been, so they can compare that to the operating pressure. So I'll do a little summary of that at the end of the presentation, okay? So this is a photo of the Jamalco alumina refinery. It's in Clarendon, Jamaica. I have never been to Jamaica. A couple of our personnel here at AFT have visited this facility. One of them did a training class back, I don't know how long ago, maybe 15 years ago, something like that, at the facility here. And so this is where the accident happened, okay? So what is an alumina refinery? And I'm gonna talk about alumina as something different from aluminum. And so let's talk about alumina. So what alumina refinery does is it processes raw bauxite. Bauxite is the raw material, and you see that down below, this is a bauxite mine where they are mining bauxite, and that is where the alumina material is embedded in that. Through a complicated multi-step process that I'm going to give you a quick summary of here in a moment, alumina is created. Alumina is also known as aluminum oxide, so it is Al2O3, aluminum oxide, and then I think some English-speaking countries pronounce aluminum aluminium, so we're talking about the same thing there. But alumina is not aluminum. It's aluminum oxide, and then the alumina is then shipped to a smelter, and then they take that raw material, that aluminum material, and they use it to create aluminum products, and that becomes the either a finished product or some sort of intermediate aluminum, which is shipped for for further processing and other manufacturing type operations. So the production of taking bauxite into alumina. The predominant method of doing this is something called the Bear process, and so this is an outline of what the what a Bear process looks like. Okay, and so I'm not going to go through all these steps, and I will tell you that I have, like I said, I have not been to the Jamalco facility in Jamaica. I have been in a alumina bauxite processing facility in South America. Taught some training classes there. They use the Bear process. And one of the things that you see when you are in alumina refinery is like everything is red because of that red color of the bauxite. And there's just everything just has a red stain to it everywhere that you go. So, but at a high level, what I want to do is say that we start here at the upper left. This is bauxite that comes in from a mine. So that is fed in to a process. And from there, the process is this multi-stage process to eventually create alumina out here at the final right, which goes off to a smelter, okay? Which is usually, it's a different facility. The alumina production does not create aluminum, it creates alumina. That's usually shipped somewhere else where they have a smelting process that goes on, okay? The point here, not to go through all these steps, but there's multiple steps where there's grinding, there's water added, there's heat added, there's pressure taken off. There's all kinds of processes as the alumina makes its way through the whole process to eventually turn out in the end, okay? So it is a complicated thing, and it's a big facility with some very tall vessels. Is there a problem?
The slides aren't advancing.
The slides are not advancing. Did you send me something on this? Okay.
No, switch to screen.
Excuse me here. So the slides are not advancing. Let me stop for a moment. And am I sharing?
Yep. And then let's see. Click on the screen drop-down arrow caret.
No. It's paused. Huh.
Let's see.
Sorry, I've got Ben here who's helping me, and we're trying to figure out what is going on. I'm trying to do monitor 2. And then you want to see what the audience is seeing, right? There we go. Should I start over?
Maybe.
So nothing is advanced at all?
No, they were stuck on the
title?
Yeah.
Okay.
Sorry about that, Trey.
Well, I don't do these. I only do these once a year. Thank you, Ben. So I guess some of this I explained, but let me go through if there's anything in here that I need to kind of summarize. We talked about this already, so I'm sorry, and I apologize for the slides not advancing. So anyway, just summarizing, this accident happened in April 16, 2016. Okay, this is a photo of the alumina refinery. And then this is just a shot I pulled off yesterday of Jamalco of the aluminum mining process, and I said everything is red in here. And so this is the raw material I talked about is bauxite, and that is what's processed, okay, through the refinery into aluminum oxide or aluminium oxide, Al2O3, and then it goes to a smelter. Okay, let me come back to the bare process so that we can see this better, okay? And so we'll restart. Fortunately, I don't have a full hour of material, probably about half an hour, so we should be good here, okay? So I'll re-explain this. The upper left is where bauxite is brought in from a mine. Multiple ways to do it: by train, by truck, by barge, something like that. It's brought into the facility and it's fed into this whole process, and you can see that there's multiple steps that goes through this whole process. The ultimate outcome of this is alumina, which is then, as I said earlier, is taken off to a different facility for smelting, okay? So this is where I was when I realized that I was not advancing slides. So we're talking about this, okay? What I want to focus on here is not the whole thing. It's first just let you know that it's complicated. These tanks are very big. There's a whole bunch of them. It's a massive facility, and everything has a red color to it when you're in an alumina refinery. Okay, so let's go on and talk about this particular area right here. So this part of the process is the part that where they're trying to drop the pressure in the tanks, and they're called blow-off tanks. So they're dropping the pressure, and they go through a series of tanks. And so this is what we care about. Then ultimately, at the end of this, then there's a transfer line that goes out to a sand trap. And I did want to say I am far away from an expert on alumina refineries and production. I know just a very little bit, and I've had a chance to actually go into one and get a tour. So that's probably the extent of what I know. So if any of you have a background in that area, you know far more than I do. I know enough definitely to be dangerous in here. Okay. Now, this particular part we're talking about here, this is where the accident happened, and the pump that failed was right there in the part going from the final blow-off tank out to the sand trap, and that's where it was located. And it was called the digester blow-off pump, and it was number 3, the number 3 pump, DBO pump, number 3. And it was part of the digestion part of the process here. Okay, so let's go ahead and dive in and look a little bit more here. Okay, so I'm gonna go down the detail and talk about this in a little bit. It's not that complicated, as you can see the diagram here, but I'm gonna outline what was going on and what happened when the event happened. Okay, so this is the digester blow-off system, DBO system. And at a high level, there's 2 tanks that are separate physical tanks. They each have 2 lines that go out, and then the lines come out ultimately through pumps, which are the slurry pumps with the digester blow-off pumps, number 3, number 4 in this case. They come through 2 valves, and they go into, this is a pressure measurement here, and then off to a long line that goes out to the sand trap, okay? This is where the number 3, this is the pump that failed right here, the number 3 DBO pump. Okay, and just if you want to look at like what the line lengths were and the diameters, etc., this gives you an idea of what these line lengths were. The ones in the purple and red are not that long. You can see we're talking about 3 to 7 meters and 9 to 23 feet. Okay, the longer line is this gold line after you go through the valves, after this pressure transmitter out to the sand trap, and that was like 105 meters or 344 feet. And you can see the line sizes range in size from 14 to, in some cases, up to 24 inches in size, or in the millimeters there you can see 350 up to 600 millimeters. Okay, so the fluid that they were pumping was a caustic slurry with a density specific gravity of 1.26. Near atmospheric pressure at the pump suction as it comes out of the tank into the pumps, the 2 different pumps. And then the discharge was about 4 bar gauge, and I'm sorry I should have given that in PSI, but it was, that's going to be roughly about 60 PSI gauge. at the discharge of the pumps. And the pumps themselves were rated for 100 PSI, about 7 bars was the rating, the maximum pressure rating in the pumps. The temperature of the hot caustic slurry was 110 degrees C, 230 F, so a little bit over boiling point, but it was a little bit over, that was because it was slightly pressurized, a little bit over 1 atmosphere, so it could hold the fluid as in a liquid form at this point, okay? Okay, so let's now talk about the operating procedure of what happened here. So there's the 2 pumps that serve the 2 DBO tanks. So pump number 3, pump number 4. I'm not going to talk about it here, but there also was a whole nother identical separate process with the number 1 pump and the number 2 pumps, and then 2 other tanks. So there was 4 pumps altogether, 4 tanks. And in general, that doesn't matter except for the fact that there was 4 pumps and there was a repair history of and service on the 4 pumps that is actually important to why the accident happened. So I will recap that more at the end. But right now we're going to talk about this part of that was called this was called the unit 2 operation. Okay, there's 2 pumps, but only one operated at a time. So we're going to talk about that in a minute. Every morning the pumps are cycled. So the reason that there's 2 pumps is to have some redundancy, like a spare pump. And so what their practice at the facility was every morning they would switch from number 4 pump to number 3. They would run number 3 for 24 hours. And then they would switch back the next day, number 4. So each pump ran about 50% of the time, every other day, and ran the full day. So the summary of the procedure over 8 minutes was and I'm going to go through this step by step what was going on, but this was at early in the morning at 6:29 a.m. local time, is that they'd have number 4 pump running and number 3 pump was off. And then what they would do is they would start the number 3 pump, then they would open the number 3 valve. So both pumps are running, both valves are open. Then they would close the number 4 valve. And then finally, they would turn off the number 4 pump. This would all happen over like 10 minutes or something, okay? What happened in this case right now is they didn't get to the final stage of turning off this pump. They closed the number 4 valve, and soon after that is when the number 3 valve, this is the one that broke, okay? So before 6:29 a.m. on that morning, this is what was happening. The purple lines were where the flow was coming from. So both tanks, the DBO tank number 1, number 2, they were both flowing from both tanks down to a combined line and into the pump. And then that was then from there going into a manual. This is a manual discharge valve. And then ultimately, as it went through, it would go out. They measured pressure right here at the discharge, and then out to the sand trap. This was the long line. These other ones, like I said, they were like, all under 25 feet, whatever that was, 7-8 meters long, each of these different lines. So they wasn't that long. I have some photos I'll show you so you can see what that looks like. Okay. Then what they did is they started the number 3 pump. So the number 3 pump was started, but the discharge valve was still closed. So it was deadheading for a few minutes until they went to open this valve. Next, when they came over, when they opened this valve, number 3, that allowed the number 3 pump and the number 4 pump to both be flowing at the same time for a couple minutes out to the sand trap discharge, okay? Their next step in the process was to go over to the number 4 valve a minute or 2 later, manually close that valve, which put the number 4 pump still in operation but deadheaded into this discharge valve. And then finally, they would turn off this pump. But they never got there that day because in the step between closing this valve and turning off this pump, in a window like of about 8 minutes, this valve broke. And the valve stem slammed shut. And when it slammed shut, that sent a pressure wave from the discharge valve number 3 back to the number 3 DBO pump, and that's the pump that actually catastrophically failed. Okay, so if you want to try to map the diagram that I just showed you onto what the physical photo looks like, I'll try to do the map on. Okay, so first let's talk about the DBO tank number 1. That's this tank right up here in the upper left. Okay, DBO tank number 2, you can't see it that well. It's in the upper right. Okay, the pumps were the number 4 pump right here. It's behind this screen right here, but this is the motor for that pump. And then the pump that failed is the number 3 pump, and number 3 pump was back behind this screen right here, and this is the motor. Okay, so the So what happened was in the one, and so this pump right here behind the screen, I'll show you some photos of it. It failed, okay? This valve right here, this is the number 3 valve, and this is the one that broke. The valve stem broke. I'll show you some photos of that. It caused the flow coming through this valve to instantly stop, and it sent the pressure wave back towards the pump, and it caused the pump to fail catastrophically. So the line coming from the number 3 pump comes out behind here. So this is the motor. The pump is behind this little wall, and it came out here, and the line came up to here, came all the way up, and then into this number 3 valve. And when it was open naturally, this valve at this point was closed when the accident happened. So, and then for scale, you can see the technician over here on the right, the scale. So these were I believe like 12-inch valves. So whatever that is, 300 millimeter size valves. Okay. Then the flow, when this valve is closed, it came from through the number 3 valve up and out. This is where the pressure measurement was, and it was not a waterhammer transient measurement. It only took sample rate, I think, was once every 4 minutes. So it couldn't tell us anything about what happened from a waterhammer point of view, but it did give us a picture of what was happening from a pressure point of view before and after the accident, from a kind of a steady state point of view. And then this line went out like several hundred feet, 100 meters or something like that, out to the sand trap. So it was far away from here. And the line went up, and it bent over, and it went off to another operation here. Okay, so when this number 3 valve broke, I'll show you what that looks like, okay? This is after they pulled it out of service. So the valve inside, this is a manual valve, and so these were the manual handle to manage the spindle inside, and this is the spindle right here. And you can see it just severed inside of here. So when that happened, it caused this disc to move inside in such a way, the fluid was coming in, it caused a disc to move and caused the fluid to come to basically an instant stop, like a Joukowsky pressurized spike, okay? And that's what happened. Okay, so this valve broke, the pressure wave then went down this line back towards the pump, and then the pump behind here will show you what happened to the pump. So this is the picture of the pump in place. So if you take a peek behind this wall here, this wall is over here on the right, I believe. Right here is this wall. And so what happened was, this is the pump casing right here. So this is the pump. It was pretty tall, like 5 feet, 1.5 meters tall, a big slurry pump. And right here, this is inside here. This is the impeller inside. You can see into the impeller. And this piece had a brittle fracture, and it blew off. And they found that piece. I'll show you to it. It found it somewhere close by. And then at this point, the pump was still spinning, and it was pulling out of the number 1 tank, and the fluid came out through here, out through this hole. And unfortunately, there was the technician that was nearby that got this sprayed onto his body, and that was the unfortunate outcome. Okay, so they pulled the pump out, and then you can see a little bit more here what was happening when they pulled it out. For scale, this is a sawhorse right here. So call that maybe 2 feet high, and whatever that is, a 600 millimeter, something like that. The pump itself was, again, maybe 1.5 meters, 5 feet high. This is the damaged pump casing right here. This is the impeller inside the pump, and this is the flow passage, where the flow under normal circumstances, it would flow through the impeller out into the volute here, and then go out through its discharge out here to the right. So let me see here. Somebody had asked about the model of the pump, and you can see now it's a centrifugal pump, and it was made by Gould's. There is some information in the technical paper that'll tell you some of the specs on the pump. Okay. And this is now just a close-up of this area right here, so you can see the damage area where there was the brittle fracture. Inside of the volute, down here, this is the impeller. This is the flow passage outside of the impeller. Another close-up on here, and this was the piece that broke off, and it flew away like I think 15, 20 feet away, 5 meters away is where it flew, and they found it. So they found this piece that blew off, and they actually went and did some metallurgical testing on this to find out what's happening from a metallurgical point of view. And there's more information on that in the technical paper. Okay, let's move on. So back in 2016, we built this model, and then in 2023, I updated a little bit, but essentially the same model that we had back in 2016 when we were helping Carib Engineering do some post-accident analysis, understanding what happened. So this is the blow-off tank number 1 in Unit 2. This is blow-off tank number 2. All this is Unit 2. We're not going to show anything here on the piping coming through the DBO, the number 4 pump. This is the number 3 pump that failed. Okay, so there was fluid coming from both these tanks. I already told you, like, these distances were like a couple meters. They weren't that long, maybe 3 feet coming through. There was the pump here. Then the distance from here to this valve that failed, that was the spindle that sheared off and failed. This was about 7 meters. A pipe right here, about 23 feet. Okay. This is the pressure measurement. And so we did all kinds of modeling. We did modeling that included the number on the other side, the number 4 pump. We did modeling of this all the way out to the sand trap. And so we drew a bunch of conclusions from that. But what I'm going to show you today is a more simplified model of that this valve closed instantly. And if this valve does close instantly, like it looks like it did, or nearly instantly, then the rest of this doesn't matter because it gets isolated. Once this valve closes, the rest of the piping and the number 4 pump and everything else, everything over there is completely isolated. So what we care about is what's coming through up to this point here and this valve closing instantly. That's what the model looked like. And then here's some predictions of pressures, okay? So the pressures right here are at the pump discharge flange. So there were some higher pressures at the valve itself, but the pressure wave came back, I said 7 meters or so, 23 feet, to the discharge flange of this pump, and that's what we're looking at over here, okay? So let's talk about flow. So the flow rate, we've got US units here on the left in GPM. Over here on the right, for those of you who are more comfortable with metric units, this is in cubic meters an hour. So the flow was a little over 4,000 GPM, about 1,000 cubic meters an hour was the flow rate initially, coming from the pump and through the valve and out, okay? And then the operating pressure was, as I said before, this is PSIG, this is bar gauge, was something like 60 PSI, something like that. I think we said somewhere it was like 4 bar gauge here. This is where the valve failed, and so we've got a couple models here. One of them is the red one, is assuming that the valve is just instantly closed, in 1 fraction of a microsecond. Okay, that's the worst case. Then we did a lot of analysis, and I mean, if I showed it all to you, it's a big report, but I'm only going to show you 2 cases here. The other one is if that valve disc, if it moved, and it not instantly, but it took 10 milliseconds to go from a full open position to closed position. And we also looked at 100 milliseconds. We looked at other different cases, but I'm going to show you these 2 just because we want to focus on this. From a flow rate point of view, we had the valve closing instantly right here. This is all in milliseconds, so it's about 4 milliseconds, and the valve closed instantly. So the flow immediately went to 0. And down here, this is like backflow, some cavitation happening in the lines, backflow coming back towards the pump. This is the instant closure. And then when the one that it closed over 10 milliseconds, we didn't see the flow coming down here out until about fully closing that valve, starting at about 4 milliseconds, about 14 milliseconds right here. And then there also had some cavitation, and the flows went negative because there was a cavity forming, which is a discussion we can get into. Okay, from a pressure point of view, that's what broke things. So when with the instant closure, we had the pressure at the pump going as high as 14 PSI gauge, which was somewhere around 90 to 100 bar gauge. Okay, the pump rating was only 100 PSI gauge, or 7 bars. So the instant closure model far exceeded the rating of the pump. The 10 millisecond one also far exceeded it. It wasn't quite as high. So this was more about like you're looking here 1100, 1200 PSI gauge, and then in bars about 80 bar gauge. Okay, again on a rating of about 7 bar gauge, or 100 PSI gauge. Okay, so there's no measurements to say exactly what happened. All we saw was the after effect that the pump exploded. And so the pressure exceeded the rating, obviously. There's some contributing factors. So one is that the pump casing, and I'm not a metallurgist, so you can probably stump me really quick on this. My co-author, second author, Sam Chamberlain, he is a metallurgist. That's his specialty. So he could answer these questions. And if you're interested in the metallurgy and the brittle fracture, send an email to me, and we'll be glad to get you in touch with Sam. Okay. This pump casing was 28% chrome iron, ASTM 532 class 3 type A. It is a subject to brittle fracture, but the material is chosen to better handle abrasive solids, because there were solid particles in there from the minerals, and so it had better wear capability. The pumps had, and I told you there was 4 of them that were all identical. They had a history of getting cracks and leaks in the casing. So they had to go back and repair those every so often. And that actually had happened in the previous 5 years. That happened 6 times. So so there was contributing factors here. And I'm always kind of fascinated when you get an engineering failure, how oftentimes it's not just one thing. It's like 2 or 3 or 4 things that all just kind of happen to kind of coincidentally line up, and that caused the failure. So a contributing factor was definitely the brittle failure nature of the pump casing material and the history of cracks and leaks. And so there was some evidence that there were some cracks in this casing, that it wasn't leaking, but there were some cracks in there that made it more subject to being overpressured and this catastrophic failure. Also, so that's the pump. The discharge valve, it had a problem. The discharge valve, this particular valve, the number 3 valve, had broken 3 times previously, and what they did is they welded it back together. So what I'm going to show you just real quick, if I can go back to this slide right here. This is that number 3 discharge valve, and so where this had the fracture on this valve stem spindle, this had been broken before, and they had welded it back together. They hadn't replaced it. They had decided they'll just weld it and go on with it. So this broke at on the valve stem in a way that had broken before. It just hadn't broken at the point in time that would cause this accident, and so it was a way that they could repair it. Okay, so getting back to where I just was, the discharge valve had broken before. So we had a pump that had a history of cracks and leaks among the 4. Then we had a discharge valve that had broken previously. And then another contributing factor was that these pumps, they would cycle them. And I mentioned this earlier, and just to kind of go back and talk about this again, is the process was to run each one for 24 hours while the other one was off, and then cycle it back on. So for the subsequent 24 hours. So with that, what that means is for every 24 hours, the pump was cooling off. It was operating at 110 degrees C was the fluid, or 230 degrees Fahrenheit. So it would pump hot fluid for 24 hours. They would turn it off. It would cool throughout the next 24 hours. Then they'd turn it on the next day. So it was getting thermal cycling every 24 hours. It would heat up, and then it would cool down on the next 24 hours. And that's part of the contributing factor here. Okay, so some conclusions. I would like to say that you could draw some excuse me here, let me get my laser pointer back, that this could tell you some real clear things what to do design and operationally, and it's kind of hard to do that. I've talked to people, and I don't know really the answer to avoid this. To me, it's not very satisfactory to say, oh, bad stuff happens and there's nothing you can do about it. So, but that's kind of what it sounds like in this case. You know, obviously, if the valve had broken before and they'd welded it, maybe one of the things is don't weld valves back, buy a new one and put it in. I don't know. When you're in an operating facility, sometimes you don't have that option. You've got to get production back up and going again, and that's kind of your best option than ordering a new one. Anyway, some conclusions are valve slam after mechanical failure can cause catastrophic system failures. I've heard of this happening in other systems as well. Catastrophic valve failures or mechanical failure of the valve slams shut, and then it causes a water hammer wave that causes some damage in the system. More attention should be paid to system design where valves can slam closed after mechanical failure. Some valves, the way they're designed, if the valve stem breaks, they're just going to go to an open position, and you're not going to get this happening. You could have obviously other implications of that. If the valve fails open and you can't close it, and you have another way to do it, then that can also have its own risks. The risk here is the valve closing upon failure and slamming closed. Okay, so when you're worried about the water hammer issues, be aware of what could happen if the valve stem breaks. Is it going to close? Is it going to open? If it opens, you might have some other options. If it's slam closed, you got to think about that. Okay. More attention should be paid to unexpected and excessive pressure surges from component failures, especially when there's personnel safeties involved. So if you have just water, it's not very hot, there's not real danger. Nobody wants a failure, but probably nobody's going to get hurt. In this case, obviously, it was caustic fluid and it was hot. And so if there's a failure and there's a spray that goes out, obviously then safety was a huge issue, and that's what happened here. This is not a statement more than a question, is require engineers to do at minimum like a Joukowsky equation calculation, just so they know what it could be. That would really be in the case only if a valve has the potential to slam shut, if there's a mechanical failure of the valve. If it's going to slam open, you've got maybe another analysis to do. But that is kind of the best that I can advise for engineers just to think about this, is what would happen to my system if the valve were to slam closed, and could it slam closed? And if it could, what would happen? And to think about that. And if it's especially a safety issue, then raise that up to the decision makers in the company to understand whether there should be maybe some alternative actions taken to try to handle that. So other than that, in this case, this facility has been in operation since the 1960s. And obviously all production facilities, they have issues, they have accidents, people, sometimes people get hurt, sometimes people, unfortunately they die. And that's obviously not acceptable. And it's not acceptable that this happened to this technician. So right now they're down operating again, and I don't know what they've changed other than there was one of the recommendations. There's a big report that Sam Chamberlain did that was to potentially use different manual valves, so that if they broke, they would actually fail into an open position, not a closed position. So that was a recommendation made. I don't know what Jamalco did about that. So that's all I have for today. I'm gonna look and see down here. I tried to answer one question here, and I'm having trouble. I'm not sure, Ben, if you're doing this, but I cannot see the questions. They're all jumbled up. So, and yeah, I don't know. Gosh. I'm trying to, oh, here we go. Now I found a way. Okay, so since we have time, I'm going to go ahead and take a crack.
Did you find them?
Is there a way to make this bigger? They're all crammed into one line.
Click on the square with the arrow pointing out at the questions. Right here.
Ah, that's so much better. I don't have to look at them all in a very one line at a time. Okay, so since we have time.
The ones are the ones that are unanswered.
Which ones?
The bottom ones, so if you scroll all the way down.
So Ben has attempted to give you some answers on these, okay? You feel like you got good answers for them on those, satisfactory?
The last three would be good if you're able to take a look at those and answer them.
Okay. So let me look at the unanswered one. I'm gonna put this over. So here's some of the questions maybe you guys can see in there. This came from Alex Yatskop. What was the root cause of slam closing the valve? And the root cause, if I'm understanding, was the pressure and flow behind the valve disc when the valve stem broke. The way the mechanical arrangement is the pressure and flow coming out of the pump discharge forced that valve disc into the closed position. And so it was the pump itself. It was kind of interesting. The pump was, the pump energy was what was used to destroy the pump. So the pump, in combination with the valve, kind of destroyed itself. A valve was closed electromagnetically. No, it was all manual. It was a manual valve with a manual handle, and they had to go and take a few minutes to actually close it. Can you go into detail on how the valve worked? Why did it fail, and why the pressure was negative? So the pressure was, let me see, it wasn't truly negative. It's just the flow went negative. I come back over. The pressure came down to vapor pressure. So you can see what happened with the valve pressure going up. It was all positive pressure, and down here it came down to vapor pressure, which was something under 1 psi, because it was a water-based slurry. At this point in time, well, you can see here we were starting to get, even on the red case, we were starting to get some flow that was negative. And what that means is that there was a cavity forming, which we can go look at, but there was vaporization, so there was boiling happening in the piping at the pump discharge, all the way to the pump discharge line. There was boiling, cold, and the boiling caused it to obviously was flashing, and then that caused vapor to happen. So this reverse flow here is what happened when the water and the slurry was coming back to collapse the vapor cavity. Okay. And that happened really for both the instant closure and the 10 millisecond closure case. Let me see. Question here also from Alex is why alternating the pumps as opposed to do planned maintenance transitions could cause more damage as it happened in your case. So it was a decision that was made that's how they operated, presumably to try to make sure that both pumps were in reasonable operating condition, that they would both run regularly. And so if there was a pump that did have an issue that had to be taken out of service, then they would not alternate. They would close that pump out, and they would let the other one run 24 hours a day until the pump that was needed service could be serviced and put back in operation. But when both pumps were assumed to be operating properly, then the operating manual procedure, which was written up as a written procedure, was to cycle them every 24 hours. I think Ben might have talked about the slurry pump. It was made by Gould's, and it was a centrifugal pump. And again, I think Ben, I guess you can, if you want to pop on. And any of these others that you feel like maybe you didn't have a total answer for, I'll try to give an answer, or we'll call it a day.
Oh, there's two new ones that just came in at the end. If you're able to see those.
Okay, were the repairs on the stem officially welded and records and testing? So I mean, they were officially, my understanding, they were, it was official, they pulled it out, they welded, they had maintenance records. Whether they tested it, I don't know the testing procedure to prove that it worked. And so, so I don't know exactly what they did other than welded it and put it back into operation. Would a rupture disc between the pump and valve stem been effective? Well, I mean, a rupture disc might have controlled where, so the answer would have been, potentially yes, and there would have been a rupture, but I mean, they didn't want a rupture disc because they didn't want to spill out the hot caustic fluid out. So really the question, maybe a better thing on a rupture disc would have been sort of a relief system. And that, if they had designed to put that in, that could have been alleviated that. Apparently this failure mode was not really envisioned by the designers. So, okay. Ben, anything else in here?
Nope, that's it, you covered it.
Okay, so thanks everyone for your attention. I didn't end up going obviously we got the late start with the slides. I apologize. So we got a 10-minute late start on the slides and then finishing up a little early. So I'm going to conclude. And if you have any more questions, you feel welcome. You see Ben put his email address up there. I will put it in the chat. Mine's not too hard to find if you Google me, but my email address is coming through the chat. Let me get it in here. And so you are welcome to email to everybody. So that is me, Trey Walters at aft.com. So you're welcome to contact me, contact Ben, and you can read the paper that was written. And if you want to understand more, and if this is something that's of deeper concern to you, I'll put you in touch with Sam Chamberlain, one of the co-authors, and he can talk. He's the one who visited the facility and did the failure report for Jamalco. So with that, we're going to call it a day. Thanks everybody for your attendance, and we will conclude from here. Thank you so much.